Hi guys, I'm Dhruva Juloori from Uber's developer platform. My work primarily focuses on handling continuous integration of changes at scale, especially in high velocity developer environments. Today I'm here to share some insights about how do we handle merging at Uber all while keeping main lines green. So before getting into the topic, I would like to get started from the problem. So why is maintaining a green mainline a hard problem? So what you see is a representation of mainline with certain commit points all being green. It means that all the checks that developers care, all the build steps, compilation checks are passing. Now we have two developers, Alice and Bob, basically create a branch from a same reference point from the mainline to introduce their changes respectively. Alice introduces change C1 and Bob introduces his change C2. Now both of them test their change in CI and both of changes pass in CI. Alice goes ahead and tries to merge his change to the main line, and the main line is still green. But when Bob tries to merge his change, the build steps fail on the main line. It is because Alice and Bob have tested their changes individually, but not collectively. Now just imagine like what could happen at scale when hundreds of developers are concurrently committing to a single repo. At Uber, we have about 4,500 plus engineers working from 10 plus global development centers, concurrently committing to 6 of our monorepos primarily, Go being the most busiest, then followed by our mobile repos, then Java, Web, and Python. Our monorepos handle a scale about 65,000 plus changes per month and are home to 1,000 plus microservices, and they facilitate 100,000 plus deployments per month and host about 135 million lines of code, or even more than that as we're speaking. So what are the drawbacks of red mainline? Basically, main being red, you would not be able to release features or enhancements or patches in production, which could directly impact the company financially in terms of cost. Hampered productivity. Developers would not be able to figure out like why their changes are failing in CI. Is it because of their change, or is it because of something else, which leads to hampered productivity and loss of time? And complex rollbacks. So just imagine like when hundreds of developers are concurrently committing and working on a single repo, it gets very hard to restore back to the last known stable state because developers might have already created a new branch and started working on it. So no company wants to be in this state because mainline being red directly impacts the company in terms of time, cost, and resources. So how do we solve this? So say hi to SubmitQueue. It's essentially Uber's MergeQueue. It provides an illusion of single queue to developers to submit their changes. It guarantees reasonable land times for developers to land their changes very quickly. It utilizes CI resources very efficiently. And of course, it always maintains green mainlines at scale, even with thousands of changes per day. So how does all of this works? Before diving deep, I would like to give a brief overview about how the system works. SubmitQueue broadly consists of 4 core components. The first one being the enumerator, which basically takes the queue of pending changes and builds the binary decision tree by speculating on the outcomes of all the pending changes. This tree basically indicates all the possible builds for those pending changes. We internally call this tree as a speculation tree. And then the profiler just takes the speculation tree as an input and ranks the changes according to the landing order by predicting the build times. Then there is another component called prioritizer, which takes the speculation tree as an input and computes the probability of build needed by predicting the success of the change and also using the landing order information supplied by the profiler. Then the selector, pretty much straightforward. It takes the top probability nodes from the trees and schedules them as builds in the CI. And based on the build outcomes, it either commits a change or rejects a change. Now let's take a working example on how all of this works and fits into a single piece. So what you see is 3 changes, C1, C2, C3, arrived in the order mentioned. For C1, there's only one possible build, which is we represent it as B1. It means that we are building change C1 against the head of the main line. For C2, there are two possible builds. So you need to test C2 in the cases when C1 has passed and also in the cases when C1 has failed. So the build steps are B12 and B2. So build B12 represents the change C2 against the head of the main line and change C1. And the build B2 represents the build steps for change C2 against the head of the main line. In the similar fashion, the chain C3 will have 4 possible builds since it has arrived after the chain C1 and C2. And we are testing the chain C3 in all the cases when C1 has passed and C2 has passed, and also the failure cases of C1 and C2. Now, if we continue this approach for n changes, the total possible builds would be like 2 power n approximately. Like this is a perfect binary tree. The total possible builds would be 2 power n minus 1. And this doesn't scale, right? Because the resources are very finite and limited. We need more smarter ways to prioritize or like determine what builds we need to schedule in the CR. So the first concept is conflict analysis. So far, we assume that all changes conflict with each other. So basically, we are building like a single tree. But if we can determine the changes doesn't conflict each other, then we could commit changes in parallel. And it also helps down to reduce the number of possible builds. The next question is like, how do we determine like the changes are independent? Well, we use build system. So the intuition behind conflict analysis is 2 changes are said to be independent if they affect a disjoint set of build targets. Meaning like if 2 changes affect the same set of build targets, they are conflicting, otherwise they are not. For example, there are 3 changes as mentioned earlier. In this case, C2 and C3 don't conflict, but they both conflict with C1. So the total possible builds for this scenario would be 5. We basically reduced builds by a factor of 2 since C2 and C3 are independent. In the previous case, they are like 7 builds. In this example, C1 and C2 are independent, but C3 conflicts with both of them. The total possible builds would be 6. And here, chain C1 and chain C2 can be committed in parallel. So just imagine at scale. But there could be cases when there are actually real conflicts. So in the times when peak load or like if there are actually real conflicts, we need more smarter ways to prioritize our builds. So we introduce a concept of probabilistic speculation, which means that we compute the probability of build needed for each node in the speculation tree instead of scheduling all the builds. So the way this works is, since for the chain C1, there's only one possible build, so the build B1 being needed would be equal to 1, which means that you 100% need the build B1 to make a decision on chain C1. Now, the build B12 is only needed when the build B1 is successful. The B1 success is dependent on the chain C1 success, which is nothing but the probability of build B12 being needed is directly dependent on the success of chain C1. Conversely, you would only need build B2 if the B1 is failed. So the probability of build B2 being needed is the failure probability of chain C1. In the similar fashion, you could compute the probability of all of the nodes, just conditional probability, and then schedule these nodes as builds in the CI by sorting based on the higher probabilities. But there is a slight challenge. So if you take this as an example, so this is a tree for 2 changes, C1 and C2. In this case, chain C1 being a very big change compared to C2. So the build of chain C1 is still in progress, but all the speculated builds of chain C2 have been evaluated and finished. So since the build B1 is still in progress, we cannot go ahead and land chain C2. It means that the chain C2 has to wait until the decision of the build B1 is determined. This is a similar example, but with more changes. In this case, all of the builds of chain C3 have been evaluated with its all conflicting changes ahead, but still the chain C3 has to wait until the builds of chain C1 and C2 have been finished. So the problem with this one is the more the change waits in the queue, the higher the chances of it conflicting with future incoming changes, which means that we basically are increasing our speculation space, which increases the number of possible builds, which we don't want to happen because it could directly impact the land times of the changes, which may lead to like very long and larger long times. So how do we solve this problem? We introduce a concept of bypassing large diff, which essentially means the changes can be landed faster if all of the speculated builds with its conflicting changes ahead have been evaluated and also yield the same outcome. Which means in the previous example, all of the builds of chain C3 have been finished and have passed in CI, while builds of C1 and C2 are still in progress. Now there's no reason for C3 to wait for C1 and C2 because all the cases have been evaluated and passed. So we go ahead and land the chain C3 because the landing order doesn't really matter. The state of the main line when C3 landed first and then C1, C2 next would be equivalent to the same as the state of the main line when C1, C2 landed first and then C3 next. It's all associative or commutative. A plus B equal to B plus A or A into B equal to B into A. So the result is the same no matter how you land. Now we want to, taking all of these assumptions, we want to prioritize our builds in such a way that we prioritize all the speculative builds for the changes that it can bypass. In the cases when a change doesn't bypass its conflicting changes ahead, we only prioritize the most likely builds to optimize the resources. Now taking these goals and putting into a mathematical notation, we derive a following formula, which means that the probability of build needed essentially depends on the build outcomes of the conflicting changes ahead and the ability of the respective change to bypass its conflicting changes ahead. The next question is, how do we evaluate build outcomes and the finish times? Well, we use machine learning. We trained two models for each of our monorepos. One is regression and classification. The classification model to predict the chain success and the regression model to predict the build times. Our models have a prediction accuracy of 97% for classification and mean absolute percentage error for regression model is about 5 to 7% on an average. The most prominent features that we use to train our models are change characteristics, like number of added lines, removed lines, number of build targets affected, status of pre-submit checks, files change, etc. And some of the dynamic characteristics like the position of the node in the tree, the height of the tree, width of the tree, etc. Now, just trying to put all of these pieces together. Basically, all the developers submit their changes to the submit queue through an API service. And then the enumerator takes these pending changes and builds the speculation trees, doing the conflict analysis using the target analyzer. And then the profiler takes the speculation tree as an input and ranks the changes according to the landing order by predicting the build times using the build time analyzer. The third component, the prioritizer, computes the probability of build needed by predicting the chain success using the success predictor and also uses the landing order information to compute the probabilities. Then the selector basically selects the high probability nodes in the trees and schedules them as builds in the CI. Based on the build outcomes, it either lands the change or rejects the change. So submit queue has been at Uber for a while now. Probably from the tail end of 2017 and 2018, we started prototyping. And after our recent enhancements of bypassing large diff and our build time prediction, we achieved a tremendous impact. Basically, we've seen like a 53% reduction of CI resources while the change volume is probably the same or even more in our major monorepos, such as Go and mobile repos and iOS and Android. Since we are building less, our CPU consumption got down by 45%. And since our prioritization model has improved, our waiting times also lowered by 37%, meaning that we are able to land changes 37% faster than what we used to before 2024. These are some of the resources that we have published publicly. Keeping master green at scale is a Eurosys paper that we have published in 2019. Bypassing large diffs in submit queue is an Uber engineering blog. CI at scale, lean, green, and fast, we have published recently in ICSC. And slashing CI costs at Uber is an Uber engineering blog. Feel free to check out them. And yeah, for any questions or anyone would like to discuss about handling continuous integration of changes at scale, feel free to reach out. And if there are any questions, I'm open to answer. Thank you.